case if you guys want to listen it again. So what I wanted to talk about today, it's this laboratory activities that now I have to do online, unfortunately. So there will be two tests that I will discuss today. So the first one is specific gravity test. And the second test will be particle size distribution test. It is also known as grain size distribution and also known as Sieve analysis. And then we'll also practice some like parts of soil classification. We'll look at different soils. Tomorrow you're going to have your quiz 2, right? So it starts from 6 a.m. Until the midnight of tomorrow. So there will be questions. There are a few questions about the test procedure. So I think it will be a good thing if you can I'm just like checking some messages. So it would be good if you can just, like watch those videos. I provided links. If you go to the week 4 laboratory 2 folder, click on that one. You will see a list of videos, and I think there are 2 videos to the laboratories, so that you can also look at the test procedure. And also there are a few sort of short tutorials how to analyze results from mostly from particle size distribution tests. The reason why is that well, a specific gravity test is not that difficult, so that's like basically like kind of like physical procedure, and well, there is still some interpretation of results. But for particle size distribution, it will also lead to soil classification, and soil classification is like one of the major parts of field investigation and laboratory investigation when we classify soil. That's why there is more information, more theory about soil classification and particle size distribution curves. Okay. So quiz 3 will be, I think, 10 questions again. So it's kind of similar to quiz 2, not quiz 3. Quiz 2 will be similar to quiz 1, 10 questions. I think there will be fewer questions like multiple choice, and there'll be questions like you'll be asked to estimate the amount of sand, amount of silt. So this is what we'll practice today. You'll be asked to get the coefficient of curvature and uniformity. Again, we'll practice it today, and look at the plasticity chart. So I don't think it's that difficult. Well, again, it's like, to me, maybe like it's not difficult at all. But if you practice today and maybe prepare for tomorrow, I'm sure you will do fine. And we'll start with the first test. This is specific gravity test. Well, I can't really explain like the whole test procedure. I think you need to watch it. And this video, it's almost 9 minutes. But I think it's a good video in terms of it shows how to prepare samples, how to perform the test, and also how to analyze the results. So if you haven't done it yet, please watch it. At least watch it before you take the quiz tomorrow. It will save you some time, because otherwise you're gonna like waste time watching videos while you are doing your quiz, and you have only 1 hour. So please watch all the videos before that. Okay, so I kind of talk about like major things, major components of the test, and the rest you'll just see in this video. So when we test the soil, we don't test like the whole soil that we collect from the field. So we actually need to sieve it. So which means that we need to remove the coarse particles like gravel, so like gravel size. And before we do the test, we prepare the sample. We sieve it through, you see this is the sieve, and the sieve is 2.36 millimeters. I hope you already know by now that it's the boundary between gravel and sand. So whatever is left here when we sieve it through is going to be gravel, and we're not going to use it. So we only use the material that will through, which is sand, silt, and clay. So this is one of the requirements for this test. The second part that we do in the test, we use this rifle box. So the idea of this rifle box to get a random distribution of particles for each subsample. So we have one, let's say, sample that, like soil sample, that we put it in this bowl, and then we pour it in this rifle box, and then we'll get two subsamples, 1 and 2. But like the way we do it, we just have like random distribution of particles. So like not like only like sand particles, only like fine particles. So it will be like random distributed, something that we would expect in nature. So this is another thing that we will do to prepare soil. And after that, we are going to put a soil in a water bottle, which kind of looks like this. Usually we fill like 1/3 of soil. This is soil. And on top of that, we're going to pour water. So water. So we just want to make sure that there is enough water to saturate sample, and then we leave it for 1 day. So for 24 hours, we don't do anything. We just leave it on the desk. Do you know why we need 24 hours? Why can't we do the tests immediately after we pour water in the soil? I mean, in the bottle. Any idea? Why do we need to wait for 24 hours to saturate? So yeah, I think we would like to better saturate it, right? So if we pour water and then it will take in the bottle, it will take some time for water to like evenly for like moisture to evenly spread out in the soil sample and saturate also evenly, because we don't want like some parts is like dry and some parts are wet, right? Okay, so you probably know what specific gravity is, right? Do you know what specific gravity, what it means, specific gravity? I'm talking about the test, but I'm not sure if you guys still remember what specific gravity means. Why do we need to get specific gravity? Anybody knows the meaning of specific gravity, or like why we use it, or what we use it for? Relative density. Not relative density is actually a different thing. Relative density is kind of shows you for like for sand or gravel, it shows you how loose the structure is. But specific gravity, we use a letter G and we put a small case s, specific gravity. So anybody remembers the definition of specific gravity, or like the meaning of specific gravity? What does it show? Why do we like put soil inside the water for this test? Okay, so specific gravity, the definition is it kind of shows you how heavy solids, like solid particles, are compared to water. And the way we do it for the definition, the one that I showed in the lecture, it's density of solids divided by density of water. So that's the kind of like textbook definition of specific gravity. If you watch the video, you will see that there is a different procedure, there is a different formula for this, but this is the meaning, like physical meaning of specific gravity. So we'd like to see how heavy solids are compared to water. And to get this density of solids, we need to know like mass of solids and this is what we can do like by just measuring the mass of dry soil. And we also need to get volume of solids. And volume of solids, it's very difficult to get, because how can we just like if we have sand or gravel or like any soil, how do we get this volume? Just only solids. I'm not talking about volume of the sample, because look, if you look here, this three-phase diagram. So we have solids here, we have water, and we have air. So this is going to be total volume. And if we have a borehole sample, we can just like measure the height and the diameter of that, and it's easy. But what we need to do is we need to get this volume of solids. And it's always very difficult to get because when we look at the structures, you will see that solids like develop structure like this, right? So they're just close to each other, but there is always some empty space. And empty space, there is always air. So trapped air. So the point of this test is we would like to get rid of the air, the one that we have in the soil. So let's say this is the soil, and we still have some air. And even if we pour some water, and imagine everything here is in water, but still we have all these air bubbles trapped in water. So we need to get rid of those air bubbles to make sure there is no air and we have only solids and we have only water. So this is the main purpose of this test. And to do that, we put this bottle in a container, and container is sealed so that we would create sort of like air cannot go in and out. And then there is a valve. We connect this valve to vacuum pressure. And then we apply vacuum pressure to suck air out of the this container and suck the air out of this water bottle. And what we actually need to do is like to get this, like suck this air bubbles out of the soil. So we put it under like a pressure. Typically we apply about 13-15 kPa of this vacuum pressure, and we run this for about 10 minutes. So we run this for 10 minutes. There is enough to get all the air out of the soil. And then when we stop the test, that like vacuum pressure thing, so our assumption is that there is no more air bubbles in the soil, and we can proceed and calculate the specific gravity. So if you look at the test, if you watch the video, and there is another thing that I would suggest. If you, I want to show you, like if you watch the video, you will see that I use spreadsheets, and I'm going to show you what spreadsheets I use, where to find them. I'm going to share my screen right now. Share application. So if you go to course content, and if you this, and if you go to laboratory 2, so you see it says laboratory 2 nodes. This is the nodes that I'm showing you right now. And then you see here it says specific gravity. So this is the laboratory sheet that I use for calculations and to record data. So mass of dry soil, I put it here. Mass of density bottle filled with soil and water, put here. So everything that all those results that I get in the test, in that video, so I put in this column, and then I use this formula to calculate specific gravity. And what I do last is we use temperature correction factor. So based on the temperature of the water that we use, we are going to correct the specific gravity. You see, there is not really much changes. The correction factor is like almost 1, very close to 1, 0.9998. It's because of the density of water. It slightly varies based on the temperature. I mean, we assume it's like 1 density of water, but for experimental reasons, like to be more accurate, we're also required to use this correction factor, which is based on the temperature. So if the temperature, let's say 20 degrees, in this case, correction factor is 1, so it's like same thing. If temp 24, whatever value of specific gravity we obtain through testing, we're going to multiply by 0.99991. So that's how it works. This one is Sieve analysis. These are the videos. This is for specific gravity test, for the particle size distribution test. And these are also videos that I would like you to watch before you do your test, because it will help you a lot how to determine the percentage of each fraction. We're going to do it right now. And also lots of things how to, that will help you as well. Okay, so I'm going back to my, if you have any questions, please feel free to ask. Share camera. Okay, so do you know what, like when we do the test, what value of specific gravity or like a range of specific gravity will be acceptable, or like something that we typically get from this kind of test? Any idea? Like what will be the number? Well, I think it was a sort of a question. I'm not sure if you're listening to me. Maybe you're a little bit shy. Maybe you don't remember, or you're just not there. Because I cannot see your faces and you're there. Anybody's there, or I'm just talking to maybe what would be the like range of specific gravity? Um, if you don't remember, that's okay, because you're not an expert. Yeah, 2.7. Yeah, 2.7, good one. If you don't remember, it's fine. There is nothing to be like embarrassed of. It just you just like need to know like where to find that information. And I think for this kind of ranges, I put all the ranges in that formula sheet, like the one that is like for first part of the course, which can be found either in those lecture summary notes, that a big PDF file with all the information about this course with different examples, or there is a separate one. If I think if you go to lecture 1 folder and click on that one, you'll see also a formula sheet. That formula sheet is very important, actually. That's all the major formulas that we use for calculations. And also that formula also has those flow charts that we're going to do today. So if you can just print it out. Oh my, that's fine. So hard to do. Okay, so um, just look at those, right? I mean, you just started this course. Maybe you don't remember. Maybe you still don't know. That's okay. So there is like nothing wrong about it. Just but make sure that like you have this information and like review it from time to time, so that it will help you like for your assessment items. Yeah. So 2.6, 2.8 is good. Um, that's even more difficult questions. Why do you think it's always in that range? Typically, like when we did this test face to face for the past several years for students, they would typically get about 2.6, 2.65. Some of them will get like 2.7. Also depends how accurate you are with your measurements. Why do you think in that range from 2.6 to 2.8. Maybe if you remember the reason, it will be easy for you to remember the range. Anybody has idea why it's in that range? Like it can be like 1.5, or it can be like, I don't know, for soil 3.5. It's usually 2.6, 2.8, or 2.7. Okay, so what I'm gonna do is I will show you this slide, and it was in the lecture I think 2 weeks ago. So the major thing, the soil, consists of different minerals, and most of soils, I think all soils, they would have quartz. So quartz is the major rock forming mineral, but when rocks are weathered, um, all other like rock minerals, they will be also changed to what we call like secondary minerals during the process of weathering. So, but quartz is not changed, so it just stays. So quartz, because it's very resistant to weathering process, so if we have it in rocks, we also have it in soil as well. But other minerals, like the one that like make rocks hard at some point and heavy, they'll be changed. So they'll be changed to sort of like what we call like clay-like minerals like kaolinite, illite, montmorillonite, halloysite. It just because of this natural process. But quartz is always like there, so it was in rocks and it still stays in soil. And typically also feldspar. Feldspar can be like, it's like feldspar is similar to quartz in terms of the properties. So, um, but quartz is typically the major mineral in all soils, and you see its specific gravity is 2.65. So that's why, well, this average 2.65. So that's why we have like range like from, let's say, 2.6 to 2.8. It like depends on how much quartz you have, and if you have some other minerals. For example, if you have some clay minerals like illite, which is so common, it's 2.8. So it kind of gives you like the average between like all those minerals that make up the soil. So but because there is lots of quartz, usually it's uh, like falls in the range of 2.6, 2.8. Sometimes when we don't do specific gravity test, we just make assumption then it's 2.7, and then we do some calculations, because specific gravity, maybe we don't really use it as it is, just like, okay, we know specific gravity and somehow we're going to use it. I mean, like somehow it gives us like lots of information. Typically, we use specific gravity to do all the calculations related to soil constituents. The one that we did last week, like degree of saturation, water content, what else is linked to densities. So void ratio. So once we know specific gravity, it's very easy for us to find out all other parameters. Okay. You have any questions? So I would really suggest watching that video, because I just upload the quiz. Well, it's not available yet, but I think there is like at least three questions related to that video. And if you know that, if you watch that video, it will be easy for you to answer those questions. Just give you some hints. Yeah, the reason that, because it's going to be like average of specific gravity, and also depends on how much quartz you have. Maybe if you have quartz 70% and you have some clay minerals like about 20% and something else 10%, so like each will contribute in regards to its percentage. So quartz would contribute the most probably to the average specific gravity of the soil. Then some clay minerals will also contribute like about 20%, and maybe like some other like minerals, maybe some kind of like calcite or something, will also contribute to according to the amount of like how much is present. So yeah, because if you look at mineral composition of soil, it's not only one mineral, it's always like 4 or 5 minerals. So typically it comes like with quartz, maybe some feldspar, which are common in all soil. And then it also depends. If you have clay, you're gonna have like 1, 2, or maybe even 3 of these clay minerals. And this montmorillonite, that's like the one that will cause lots of problems. Or if it's sand, maybe it will be like mostly quartz, some feldspar, and maybe like very small amount of some like clay mineral, like very, very small amount. So in this case, specific gravity will depend again on those minerals. So it's not only one mineral. So it's kind of average of those minerals, and it depends on how much, like in terms of percentage of each mineral is present in the soil. Okay, well. So next test is particle size distribution test. It's like a really long test, but it's pretty simple. And I think it will be like really good for you to. This is like one of the basic tests. Like when you work in the industry, like geotechnical, this is something that you will do, or you'll ask somebody like a technical stuff to do. This is like probably like test number one that geotechnical engineers do, like when they do site investigation. It's pretty simple. We have sieves, and the sieves, they have all different openings, so what we call mesh. So it's kind of like this. This is a coarse one, or really, really fine one. So this mesh will define the size of particles. And then we'll like set it up as like a stack of sieves. Like we have a lot. So the last one, the one that we put at bottom, it's called pan. It has no openings, no mesh. It's just like a pan to collect everything that goes through the final sieve. So typically it comes before 0.075 millimeters. And somewhere here we have 2.36 millimeters. So these are the major sieves that we would like to use to get the difference in terms of fractions. So as you know, everything that, well, sorry. So first we'll start with the test. We have some soil. I think it's about 200 grams or 250 grams. I need to check the video standard. And then we just pour it on the top of the stack of sieves. And then some soil will stay here because it has bigger particles. Some will go through. Then maybe stay a little bit here. The rest will go through. Maybe here, and then here, and maybe even more here. So what we do is we before we do the test, we just measure the mass of each of the sieve, like let's say M1, M2, M3. Then we do it like we perform the test, and then we like disconnect those sieves, like separate them again, and then we measure the mass of each again. So it's going to be M, let's say -1, M-2, and then we take the difference in terms of mass of the sieve with soil and without soil. And once we know the amount of soil, let's say here we have maybe 20 grams of soil. Here we have, in this sieve, we have 15 grams of soil. Here maybe we have a lot, like 45 grams of soil. Here 50, and here maybe only 3 grams. So altogether should be the same amount as we put in when we do the test. And then we just get the percentage compared to the initial mass of the soil sample that we use. And we get the percentage, and we just draw it as a grain size distribution curve. I will show you later how to do that. So basically, that's about it in terms of the test procedure. I'm not going to ask you to, for this particular test, I'm not going to ask you to do this like the test analysis, like in terms of changes in the masses, like the one that I want to show you. So I want to show you example. Again, I'm going to share my screen with you. Application share. So this is Sieve analysis. So the one, like when I do the test in the video, I put all the information in this table, and then I work out each column, and then I draw like whatever numbers I have here in column 7. I plot it against data from column 1. So you will not do this one in quiz, so because it will be like lots of time for you to do. But I would like you just at least like to watch the video and see how it like how it's done. And another thing is I put example of Sieve analysis. So this one you can actually find in my textbook. If you haven't done it yet, you can go to online Griffith Library and download the PDF file. There is explanation, and this is also I also explain in that video. Sorry, not in that video, in the book, how we get the numbers and how we do these calculations and how we draw a curve and how we do everything. So whatever I'm talking about today, it's all in that book. You guys know the name of the book? Do I need to tell you the name of the book again? It's I think what you can do is if you let me see what you said. You don't know the name of the book? How come you don't know the name of the book? That's like the best book for this course. Look, if you go to readings, right, you can probably see, right, what I'm doing readings. And then the way that I do it, I'm not sure you should be able. And then it says so mechanics through project-based learning. So that's the readings and view online. So just view online. You should be able to download it. It takes you to the this page, and it says download, so it's free or read online. So download this book. All the information, like even like how to do projects, something that you're going to do, it is all there. So it will be like a great help to you. Okay, so it's called Some Mechanics for Project-Based Learning. Yeah, I think that would be good. I'm going back to my slides. You said no need to tell. Sorry, guys. I didn't see like I didn't see your chats. So okay, you know the book, well, which is good. Okay. Maybe for those maybe for those who don't know yet. So I think it's a good. You see share files. Okay, so now let's get to some practice. Let's get to some practice. So this is the kind of results that we get from this test. And what we'll do now is, well, you will see how to draw these curves. And then we'll start getting the amount of each fraction, different coefficients, and classify this all. So this is what I would like to do in this laboratory. So in this case, you will see that we there's 3 soils. Sorry, 4 soils. So A, B, C, and D. And here it says results of hydrometer test. Hydrometer test is a different test. It's not like this particle size distribution or Sieve analysis. I talked about the test in the lecture where we have like fine particles sort of floating, swimming in the, liquid, and then we measure the density of that liquid. and based on the velocity, so how fast those fine particles settle. So based on that one, we measured the velocity of those particles, and based on the velocity, we have theoretical / empirical correlations to the size of the particles. So that's how we do it. It's indirect methods of getting the size of the particles. And you see this one, it's Sieve analysis. And this part, it's a hydrometer test. You will notice that we only have data for hydrometer test, for soil C, and for soil D. Do you know why we only did soil C and soil D? Anybody would like to tell me why it's only for soil C and soil D? We didn't do it for soil A and for soil B. What's the reason? Fines, yes, fines. So to do this test, we need to have fines about 10% or higher. So if you have less than 10%, then we're not going to do this test. Yeah. So, okay, just another question. What is the amount of fines in soil A? Soil A, this one. Can anybody just by looking at the data? I taught you before how to look at the curve. So I want to also show you how we can do it just by, which is even easier. We'll look at the data. So can you tell me what is the amount of zero? Yeah, very good. So remember, fines the boundary between coarse grain soil and fine grain soil, it's 0.075 millimeters. So everything here is going to be gravel plus sand. Everything that goes down is going to be silt plus clay. So if we say finer, it means that soil, like there is soil which is finer or smaller than this size, 0.075. And in this case, we see that 0 is finer than 0.075. So which means like no soil is finer than this one. So you see it says it's percentage fine, which means that all the data here, it means the amount of soil which is smaller, like the size of that soil is smaller than 0.075. So you see that for soil A, it's like we have no fines at all. That's okay. For soil B, we have 3%. But for soil C, we have 34%. So we have more than 10%. So that's why we do hydrometer test. And this one we have 95%. So in this case, again, more than 10% we do hydrometer test. Okay. So how much clay in soil C and D? Can you tell me? Just by looking at again at this. How much clay do you think in soil C? So you still like need to remember the boundary. 30, no, clay, not 30. 7, yeah, 7, good. And for soil D? For soil D, 31. Okay, so very good. So you see that again, what you just need to remember, or if you don't remember, always look at the notes, the boundary. And the boundary here is 0.02 millimeters. So everything that is finer, so goes this way, is going to be clay. So if you have a finer, like again smaller, like less than 0.002%, sorry, 0.002 millimeters, it's going to be clay. So in this case, you will see that we have 7%, which are finer or smaller than this size, and here we have 31. So we have clay 7% and for soil C and 31 for soil D. Okay, so it's actually a little bit easier in terms of the numbers, that's this information from the table compared to like curves. But in your quizzes, you always look at the, you will, I'm going to give you curves, not data table. Okay, so, and okay, so let's then do, like we already did, let's do gravel. If you look at the table, right, for soil A, like soil A, can you give me how much gravel we have, just looking at the numbers. $76 gravel. 76, yeah, that's correct. So, and then what about sand? Then for soil A, what about sand? I think it's going to be the like remaining to make it 100% 24, yeah. Okay, so again, to do that, just need to remember the number 2.36, right? So this is the sort of magic number. We would define gravel like a line between gravel and sand. So everything that is finer, like in this case, out of 100% of the soil that we sieved, 25% was actually smaller than the size of 2.36. It was finer. So which means that 76% was actually, in terms of the size, it was greater, right, than 2.36. So if we had 100% that we started, 100% of soil, and then 25, it's finer, which is smaller than 2.36, 2.36, like smaller. So in this case, that 76% is greater, and we know that everything that is greater than 2.36 is gravel. And then what we do next is for sand, we take 24% because we know that like the remaining percentage is 24 because 76% it's already like gravel. So it's already like stuck in that sieve of 2.36 millimeters or like even greater sieves. So in this case, we know that only 24% left. So it can be sand, silt, and clay. So to find sand, we're gonna have this like the remaining 24 and subtract the amount of silt and clay or fines. And we know that fines is 0, 24%. You just make sure that fine 0, make sure that when you sum it up, it's 100%, not 110 or 101 or 99. So make sure to do that, right? Want to practice with cell B? Can you give me the amount of for cell B? Let's just do like cell B and then we just go to the curves. Can you give me amount of gravel for cell B, sand, and fines? 2 gravel, yes. For gravel, it's going to be 100 minus 98, which is 2%. And how much sand? 95, correct. 98 minus 3, 95. And the fines? 3%. Okay, that's very good. Just make sure 2 plus 3 plus 95, 100. Okay, well done. So you can do the rest for cell C and D, but in the quizzes, you are given these curves. So we're gonna do the same thing. It's like basically like same thing. It just we get those numbers not from the table. We get it from the curve. For the quizzes, you don't need to draw these curves, but for project one, you'll be asked to draw curves. I would like you also to practice how to draw curves because for all geotechnical reports, they present data in a table and they also draw curves. So curves like this one. When you draw it for your project, what you can use just Excel. If you want to draw by hand, it's fine. Just make sure that for this particle size, you have a log scale, logarithmic scale. So this one percentage finer or smaller, it's a regular scale, so don't worry about that one. The way that we draw this curve, we use grain size, which comes from the sieves. So this is actually like the size of the mesh in the sieve. but we use it as size of particles, and we draw it against percentage of finer. So this is going to be for soil A. For soil B, it will be this one, soil C and D. And if you use that, we have soil A, B, C, D. When you look at your questions in the quizzes, you will see that there is also points here. So I drew these curves, those curves in Excel, and this is the points that I used to draw the curves. These points come from the table, right? So we know the size and we know the percentage, and we draw it like that. Is it clear? Okay, so if it's clear, that's fine. Now what we can do is let's just do one of the soils. We're not going to do A and B because we already have some idea how to do that. Let's do soil C. And for soil C, we are going to we're not going to look at the table. We're just going to look at the curve. So it's something that you'll do tomorrow. I want to do a quiz. Okay, so let's decide how much gravel, sand, silt, and clay we have for soil C. And the way we start is we start with the boundary between gravel and sand. We usually start with like coarse grain material, and that will be here 2.36 millimeters, right? What we need to do, I think the best way for you is if you can print out those questions and do it on a paper. It will be easy for you. Well, if you cannot do that, well, that's fine. Just like do it on the screen, but try to be accurate. So in the questions, the range allowed for your answers for this type of question is 1%. So you should be try to get it in the range of 1%. So if it's like my answer is, let's say 41%. So if you say like 40 or 42, it's still okay, or 41.5. But if it's like out of the range, you may lose the mark. So and that's why I would like you to do as accurate as possible, so that you can keep those marks. Okay, so we'll start this one. We'll start with 2.36. Next one, boundary, it's 0.75. So it's going to be 2, 3, 4, 5, 6, 7. I believe here the last point should be 0.75. Something like this. And if you want, you can write in your notes 0.075. And the last boundary, it's 0.002. That's for clay. So what we know that this is going to be gravel, this is going to be sand, this is going to be silt, and this is going to be clay. So what we do is now we look at the curve. We're doing C, right? So C. Let's see how much of each fraction is there. So remember, we got those numbers from the table. In this case, we actually have to get them from here. 60. Well, this is actually needs to be a little bit down, right? Okay. Okay. Let's say like it's about 60, right? I think it should be a little bit below 60, but okay. This one, second one, will be like somewhere here, and the last one, it's here. Well, again, a little bit higher, maybe like this. Okay, so you see like what I did, I just look at the percentage finer for like those points. You see I have point here. It's point where this boundary 2.36 crosses the curve, then the second boundary crosses the curve, and the third boundary crosses the curve. So we'll try to estimate it as accurate as possible. And then here, let's say, well, it's about 60%. All right. Here, well, I would say about 38, right? And the rest will be, what about, I think it should be about maybe 7. Didn't draw it very well, but 7%. Okay, so now we calculate gravel. So gravel, it's 100 minus 60, 40%, right? Then sand, we have, we started with 60 minus 38. It's, I think about 22, right? 22%. Then fines, well, sealed, it's 38 minus 7, 31%. And clay, it's just 7%. So that's what we have. So that's how you get all the percentage. Try to get these numbers as accurate as possible. That's my only advice to you. I mean, for me, it's a little bit difficult to draw it on the screen. They may be plus minus 1 or 2%, but I think for your test, you should try to do it as much as you can. You have questions about how we get percentage? And we'll do the same for other soils. I guess we'll just do this one first. Okay, well, I'll take it as no questions. And then I'll just take you to the next slide. Well, this is something that you should, well, if you don't remember, at least you know like what it means and like where to get all the information. These are the boundaries for different systems. So this one is Australian system, the one that we use in this course. This one is British, and this one is Unified Soil Classification System. So the major difference, we kind of use this one to classify soil, and in Australia we use this one. So these are two major ones. You'll see that this is the same. This one is different. You see, like in Australia, we say that the boundary between sand and gravel is 2.36 millimeters, but for a unified soil classification system, it's 475. So just please be aware of this difference because this is important when we classify soil using this classification system. So the boundary is not going to be 2.36 anymore. It's going to be 4.75, and we'll do it later today. So remember 4.75. You determine the amount of each fraction. You just use Australian system. If there's a question, please give us the percentage of sand. So in this case, you still use Australian system to like what we did right now. You do the same thing for your curve in your quiz. Okay. Then I'll go to next. Okay, good. Next slide. So particles. Oh well, what we did this exercise? We put the numbers. One of like we did like A and B for like using just the table, and we did C just right now to get percentage of gravel, sand, silt, and clay. So what I can do, just like for soil D, you can guys maybe practice home. I'll just try it for soil D. Do you have any data? So for soil D, it will be gravel. It's 0% because the boundary is 2.36 here, and you see curve like starts from this point, so there is no gravel at all. And there will be 5% of sand. There is lots of 64% of silt and 31% of clay. So I think maybe this is something for you to practice if you want to practice a little bit more, either before tomorrow quiz or when you have 10% quiz. There are always questions to classify the soil, and to classify the soil, you still need to know the percentage of gravel and sand. So this will be like a good idea for you to practice a bit more. So these are the numbers. And then we'll actually come back to these numbers when we classify the soil. So I'm just not going to do it again because this is kind of same thing that I already talked about today. Okay, this is a different thing. And again, this is something that you'll be tested in the laboratory quiz tomorrow. And again, this is a part of classification procedure, something that you will do again for your online quiz in week 6. So you need to get these coefficients. And the thing that you should remember, these coefficients we get only for coarse grained soil, which is not plastic. So if it's non-plastic soil, there is no plasticity. In this case, we use these coefficients. If I have a soil like soil C and D, they actually come with some data on plasticity. And I'll quickly go back. You see, like this is the initial data that we get from testing. And here we have, it says soil C has liquid limit and plastic limit. Soil D has liquid limit and plastic limit, which means that these soils are plastic. So we're going to have another laboratory in week 6 on how to do this test. I already uploaded those videos, how to do liquid limit test and plastic limit test. You can watch them already. But this will be like in a few weeks, in week 6. So these are plastic soils. For these two soils, we are not going to do this coefficient gradations. So we're going to do only for soil A and B because they are not plastic. Please don't waste your time and do this coefficient CU and CC for soil C and D because it's not necessary. I've seen many students doing that, even though I told them not to do that. I say, well, for plastic soil, we have a different approach to classify the soil. But for non-plastic soil, we need to find CU and CC, these two coefficients. And to get these two coefficients, we need to just look at the shape of the curve. So soil A and B. And like the way that like we try to characterize the shape of the curve, we look at 3 points on this curve, and it's decided that it will be a point which is, we'll call it D10, which is correlated to it's the size of particles which are finer than 10%. The other one is D30, and this one is D60. So we just need to look at 3 points. Let's look at, do it for cell B, 0.1, 0.2, 0.3. And then we just like see like how close they're to each other. I mean like wider or closer. And based on that, we just gonna say if the soil is well graded or poorly graded. So when typically like these points are like far apart from each other, in this case, most of soil is well graded. When they're close, like in this case for cell B, most likely it's going to be poorly graded. But again, that's already, I'm talking from my experience, but like the correct way to do it, we need to get this coefficient CC and CU. And based on these coefficients, we will decide if it's well graded or poorly graded. So let's do this D10, D13, D60. We only do it for cell A, for cell B. Again, you can practice home and get a bit of practice more. So for this one, it will be about 0. 0.23, and right here 0.23 millimeters. The second B is right where we have here 0.3, and D60, D60 a little bit more than 0.4, like probably 0.41. 0.41. Then if we put the numbers in the formula, the coefficient of uniformity, CU, it stands for coefficient of uniformity. It will be 1.8. And the coefficient of curvature will be 0.95. I already have data for soil A, just write it down here, but maybe you can practice later on by yourself. It's about 0.47. For D30 will be 3.5. And for D60 will be 16. So in this case, the coefficient of uniformity it's 34. And coefficient of curvature 1.6. We will need this information to classify the soil. Is it clear how to do this? You have to do it by yourself. Yes, okay. So take that as yes. Okay, so then we'll just go to next part of the presentation. And this one is how to use the plasticity charts. There is a video I recorded, explanation of how to do that. It's actually like short video, only like 4 minutes. So when we have soil that is not plastic, like soil A and B, we do the gradation. And when we have information on plasticity, like for soil C and D, we are going to use this plasticity chart. So we don't need to do gradation anymore, but we need to understand how this plasticity chart works. So it's written like drawn as liquid limit versus plasticity index. Please pay attention. This one is plasticity index, which is PI, and PI is the difference between liquid limit and plastic limit. What you are typically given is plastic limit. So what you need to do first, you need to find plasticity index. So let's find plasticity index for soil C. So plasticity index will be 26 minus 17. It will be 9%. And let's also do the other one for the soil D. Plasticity index, it's 42.5 minus 24 will give us about 18.5%. So what we do now is we're going to look at the chart and locate 2 points and see if it's above or below A line. So this line, this is called A line. It's a line that defines clay and silt. So every point that we have for soil, which is above A line, ECC, is going to be clay. Everything below A line is going to be silt. M stands for silt. And also we have gradation based on the liquid limits. So we have low plasticity, then 50 we have intermediate plasticity, more than 50 we have high plasticity, Then here we have very high, and here we have extremely high. And the same also works for silt. So we classify it based on, well, we can tell if it's clay or silt, and we can also provide more information if it's low plasticity, intermediate, high, or very high. So let's look at these 2 points, and let's look at first soil C. We have a liquid limit of 26, somewhere here 26, and this one is going to be 9. So it's actually above the A line, and the classification will be CL. Let's look at the second soil, soil D, 42.5. It's somewhere here, and 18.5. 18.5. Where did I put this one? Just want to look at my notes how I classified before, because it's always like there's few things that are always on the boundary. Still looks like this. 42.5. Well, I think this will be more like above because it's almost like 19. So CI, yeah, okay, good. CI. So it's above. This is going to be CI. If you're kind of like not sure which is on like top or like above or below, I will later on show you the formula, but you can just do like put like numbers in the formula, and then it will give you answer if it's above or below. So, but the easiest way, you just look at the chart. Okay, so this one is going to be CI. So do you think you can do this by yourself, this classification? Okay, good. So then we'll just go to next step. Okay, and what we're going to do next is we'll just practice how to classify the soil. There are 2 systems. So the first one is AASHTO classification system, which I think it's more detailed. And I like it a little bit more because it's easier to use. It's developed in terms of flow chart. So you start from the top box and work it out all the way down. So based on the information you have that you have obtained from the test. So what you need to remember is for this AASHTO, you have coarse grain soil and fine grain soil. So you have 2 different charts to use. And how you know which one to use is you look at the percentage of fines. So in this classification, you see F means fines, and you look at this percentage. If it's from 0 to 35% fines, it's going to be coarse grain soil. You're going to use this chart. If it's more than 35%, from 35 to 100, it's going to be a fine soil, and you will use this chart. So you see that for each soil, when we classify it, it's very important to know the amount of fines, not just clay or silt, so clay and silt together. So it will give you the amount of fines, and after that, you just classify the soil. So let's go ahead and start classifying soils. Well, there are also 2 videos for AASHTO. I did one for coarse grain soil, how we classify it, and part 2 is for plastic soil. There are slightly different ways to classify it. I think it would be good if you can just watch those videos. If you don't understand how it works, or you want a little bit of more information, a little bit more practice, I think I look at a few examples in each video, so that will be a good help for you. Okay, so now we are going to classify these 2 soils, soil A and soil B. This is all the information that we have obtained so far. So we look at the percentage of each fraction, right? Remember that for soil A, fines was 0%. And then we also did D10, D30, D60. and soil gradation, and then we obtain those coefficients: coefficient of uniformity, coefficient of curvature. And we did the same thing for soil B. We have amount of gravel, sand, and fines 3%. And we did the same thing, coefficient of uniformity and coefficient of curvature. So this is what we need to classify non-plastic soil, right? So let's just start. I'll do soil A first together, and then maybe just you can try to do soil B by yourself and just tell me the answer. So the way it's going to work is we'll look at the fines, and we know it's 0%. So okay, we make sure that's the right chart, because it's range from 0 to 35. Then we're going down, and we need to decide either we're going to the left or we're going to the right. So you see here G stands for gravel and S stands for sand. So we just see which one we have more. We have more gravel. We have 76% gravel, right? 76 versus 24 of sand. So we're going this way. So, and then we need to decide again, we look at the fines. Fines from 0 to 5%, 5, 15, or 15 to 35. So we know that we have 0% fines. So again, we're going to the most left. And this gives us the answer gravel. Well, this is not enough. We need to classify it based on its gradation. So you see you have two options, GW and GP. So you don't really need to say GPU or GPG. That's already for like maybe like advanced users, if you can say like that. So if you just classify it, if it's well graded or poorly graded, that will be good enough for me. So to do that, we will need to look at the requirements for well graded soil, and we know it's gravel. So we're going to look at this one, gravel. So for this soil to be well graded, so this coefficient of curvature needs to be in the range from 1 to 3, and the coefficient of uniformity must be more than 4. So we need to meet both requirements. We see that we have coefficient of curvature 1.6. Yes, this meets the requirement, plus, and the coefficient of uniformity for this soil is 34, and we need more than 4. Yes, so it also meets the requirement. So then the classification of this soil will be GW. So that's it. So that's what I need you to do when I ask you to classify the soil using this classification system, AASHTO classification system. Okay, can you now like try to classify soil B by yourself? If you're still there and listening to my presentation. I'll just erase all this so that it doesn't stay in the way. SP. Very good. So it's going to be SP. Okay, let's then do it together. So we have fines 3%, right? So that's correct. We're going to use this flow chart. Then we have sand 95% versus gravel 2%. So in this case, we have more sand going this way because there is more sand. Then we have fines 3%, which is going to be this box, 0 to 5%. So we know it's sand. Now we're going to look at the gradation for sand. We see that CC should be from 1 to 3, but we have 0.95. Okay, minus. So in this case, if one criteria is not fulfilled, in this case, it's already poorly graded. So SP. So that's the answer. Um, just, well, it's not required, but out of observable difference, if I'm looking at poorly graded sand. Okay, so this is a good question. What is the difference? So you know that when we have well-graded soil, we have particles of like different sizes with kind of a good distribution. No, I think it's sometimes it's very difficult. It's not as going to be heavier or it's not as going to be different color. Color like typically depends on the origin of soil and it's not going to be heavier. But what you can do is you can just look at the curve and well, curve will already tell you if it's poorly graded or well graded. So we look at soil B, right, the one we classified. You will see how it goes all the way up here. It sort of like fits in like very like narrow range. So basically it's, I think, remember sand was about 95%. So what it tells us is going to be like poorly graded, yeah. So it's uniform. It's one of those like uniform. Uniform when we have one dominant size, like size of the particles, like mostly like same size. Like in this case, we have only like sand, mostly sand. So this is going to be uniform. When you look at A, this one, you see how it goes through like these like ranges and like more or less evenly. You know, you have like here, here, and here. So it's like more or less like better distributed, like well distributed. So this is like an example of well-graded soil. So what you can do, you just like look at the curve, you already can tell, well, this is definitely going to be like a uniform, poorly graded, and this one is going to be like most likely well graded. So this is how you can tell. Sometimes when you deal with a sand, like maybe like a beach sand, you will see that like you can like see this like sand particles, they're all like about same size. In this case, you can say this is probably like poorly graded, is going to be uniform soil. Sometimes you see like like bigger particles of sand and gravel like mixed with like medium small size. You can probably have some idea that is going to be like well graded. But again, without this proper test, it's very difficult to give the correct answer. So you can kind of guess. So if the same particles, same size, and like clean, like sandy, like clean beach sand. So that's probably like good example of a uniform material. So like because you see like those big particles of sand and you don't see like much of the fines and gravel. So you know it's going to be that. But in terms of color, I don't think it's possible to based on the color because color it's kind of shows like slightly different properties. I mean, comes maybe from the type of mineral or like where it was originated, things like that. Okay, so what we do next is we did soil A and soil B. Now let's do soil C. And for soil C, we had this liquid limit and plastic limit. And remember when we already did this one, right? We got plasticity index of 9, and then we classify it as CL. Remember we already did CL. So now that's CL. Okay, so now let's classify this soil C using this AASHTO classification system. So again, the first thing that you need to do is you just see how much fines you have. Fines, it's silt plus clay. It's 27 plus 7 will give you 34. So it's still, oops, it's not this soil anymore. Okay. So how about we just, it's still 34%. I put different chart. How's the PI CI when PI is only 9? I think that's what we did because liquid limit was 26 and plasticity index was 9. So it's above, so it's going to be CL, clay flow plasticity. Because intermediate plasticity, it's when you have liquid limit from 35 to 50. It's going to be intermediate. So if you see like it's 35, it's less than 35. In this case, we have 26. So we know that it's already low plasticity. We just need to decide if it's clay or sealed. If it's above the A line, it's going to be clay, and that's what we have, clay. So it's CL. I'll have to go back, but to the other chart. But don't worry, we'll just classify it. So what I'm going to do now, I'm going to write this soil C. We have a gravel of 41%. We have sand 25%. We have silt 27, and we have clay 7%. And we know that it's CL, right? Clay flow plasticity. Okay, let's classify this soil together. So still we're going to use this chart because we have fines altogether 34%. So then we're going to look at what we have, more gravel or sand. We have more gravel going all the way here. Gravel, we have more gravel, right? Then next is going to the right because we have fines 34%. And then we come to these two options. And this is where students make mistakes. So what they do is, you see, you have option like silty gravel or clay gravel. What they do, they just look at what you have more, silt or clay, and then they say, okay, it's going to be silty gravel, and that's the end. So this is incorrect. We classify soil if it's silt or clay based on its plasticity, not based on how much silt or clay we have in it. So, and we already did this one. We already know, we already knew that it's clay, because when we look at the plasticity chart, that point was above the A line. So in this case, we know it's clay. Even though here we have more silt, 27, the soil is classified as clay. So please don't make this mistake. Like about 20-30% of students make this mistake because they probably don't listen to me, or just don't, like basically don't listen to me. So in this case, yeah. So what we do next is we're going to find where we have CL in these symbols, and there is only one symbol that actually has CL, is this one, GCL. So it's going to be the answer, GCL. And this is how you classify the soil. Okay, so just like, don't make mistake, don't look at the how much silt and clay you have in terms of percentage. Everything, if you have plasticity, so you will need to come up with one of those symbols here, not just like definition like very silty gravel. So in this is very important. Okay, then let's do CLD, and then we still need to look at other classification systems. So in this case, I mean, maybe you can do it. You can do it by yourself and just tell me what you think. We already did this classification, and it was CI. Remember, I think point was 42.518, somewhere here. It was CI. Do you think you can classify this for me just using this classification system? That's CI, yeah, that's correct. Okay, so yeah, okay, good. So again, we'll start with the fines. Fines, the most important thing. We have clay and silt. Altogether, fines will be 95%, correct? So it goes 95 goes all the way here. And then we're going down. Again, we don't look what we have more in terms of percentage seal to clay. We just look at the plasticity and we know it's CI. And we look for CI. CI is here. There's only like CI available, so the answer will be CI. So that's the final answer for this, so how to classify soil D. So do you get some idea how to use a classification system? Again, if still like something like unclear, just watch those like short videos that I recorded. It's like I explain again like the difference between plastic soil and non-plastic soil. Okay, that's good. So we have the last task for today. We have another classification system, which is also like very commonly used unified soil classification system. It has like very similar kind of like setup, like the concept to classify the soil. And I think it's a little bit easier compared to the other one. But there's few differences, so that I would like you to be aware of that. So I remember for this AASHTO soil classification system, the like borderline was 35% of fines. So 35% that was coarse grain and fine grain soil. So in this case, the boundary between coarse grain soil and fine 50%. So it's kind of 50-50. So if we have less than 50% fines, so you see it says this one is soil passing through the sieve. The sieve it's called number 200. So it's correlates to the size of 0.075, which is the boundary between fine grain soil and coarse grain soil. So if we have amount of soil like that is passing through the sieve, and it's like less than 50% passing through the sieve, which means that we have more than 50% which actually like retains in that sieve, which is 50% sand and gravel. So we're going to use this top part of the chart. So this one is going to be sand plus gravel. If 50% passing through this sieve of 0.075 millimeters, this means that there is lots of clay because it's like more than 50% fines. We're going to use this chart. I mean, not chart, this bottom table. So next one, which is important. So this is kind of similar, right? You see like if you have more fines, then it's going to be fine soil. If more coarse material, coarse grain soil. But the boundary is 50%. And another difference here is, remember how for the other classification system, we see what we have more sand or gravel. We'll basically do like same thing in this classification system, but we are going to change the boundary. So the one that we used in Australian standard, we use 2.36, but here it's 7.75. Remember in the beginning of the lecture, I said 4.75 when we look at the boundaries of each sizes. And I said that for a unified soil classification system, the boundary between gravel and sand is 4.75 millimeters compared to Australian standard, which is 2.36 meters. So this is like another major difference. So in this case, we will have to go back to the curve, and we will have to re-estimate, re-evaluate the amount of gravel and sand. So in this case, if let's say curve was like this, right, and we have 2.36 boundary, and we were saying everything here will be gravel and here will be sand. So in this case, we're going to move the boundary to 4.75. And then this is going to be everything here on the right is going to be gravel, but from here it's going to be sand. So basically what we have is, so basically what we have here is here on the left-hand side, I mean, we'll probably have like more sand. We're going to have more sand when we use this unified soil classification system compared to like when we use the other system. So this is another major difference that you should be aware of, this 4.75. Then third column is we look at the, again, percentage of fines. 0.5% is the same as AASHTO. Here we have a little bit different. This from 5 to 12 and from 12 to 50. So we have 3 boxes. Then for soil that is 0 to 5%, we're going to decide if it's well graded or poorly graded. So we're going to answer this question, yes or no. And then we also see if it's above or below. So what I'm going to do now, we're just going to look at the soils that we have. We have some time left. Let's try to classify those soils again, but in this case, we're going to use this unified soil classification system. So these are for soils. What I'm going to do is I got these numbers like gravel and sand based on the boundary of 2.36 millimeters. So this is okay when we use AASHTO soil classification system, but we have to recalculate these numbers. So I'm not going to do it. I'll just assume that they're still the same. But you shouldn't do that when you like work on your project, because I don't have time to do that, and you probably already know how to do it. So basically, in this case, maybe we're going to have more sand than gravel because we're going to look at a slightly different boundary. But let's just assume that we had this data and we use this boundary 4.75 to define sand and gravel, right? So we just make this assumption because I just want to show like how we use the chart, but this is kind of small details that you can probably like work out by yourself when you're asked to use this classification system. Just remember that gravel and sand it defines as now 4.75 millimeters. Okay, so let's start with soil A. So A, and again, we look at the amount of fines, and fines we have 0%, which means that it's less than 50%, right? I mean, 0 is less than 50, so we use this one. If you're not sure if it's, well, I mean, you're probably sure, just look at the amount of fines. So next step is we're going to compare amount of sand and gravel. So if we have more sand or gravel, so if we have more than 50% of that coarse grain material that passes through the sieve, in this case it's going to be sand, because like more than like half like pass through the sieve, it means that like more than half of the soil is sand. So we're going to have sand, and you will see that all your answers will be here: sand, 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 sand. If you have less than 50% that pass of this coarse grain material that pass through the sieve 4.75, in this case we're going to have gravel, right? So we see that we have more gravel. So we have means which means that less than 50% pass through this boundary. Next step is we look at the amount of fines again. We have a 0% fine, so it's going to be from 0 to 5%. And now, like same thing as we did for the other classification system, we'll look at the soil gradation. So we just need to answer this question. So do we have CU more than 4? Yes. Do we have CC in the range from 1 to 3? Yes. So in this case, answer is yes. And the classification is GW. So you'll see it's actually the same classification as we got using the other classification system. How about you try to do cell B? Can you do cell B by yourself? Just let me give me an answer and then we'll just do it together. SP. Okay, so let's check if it's SP or not, right? So again, we'll look at the amount of fines, 3%. So it's less than 50%. So this amount of fines less than 50%. Then we have more sand, so which means that more than 50% of the course material pass through this boundary between gravel and sand. Yes, so it's going to be here this way. Then we have 3% of fines. It's in this box. And then we're going to answer this question: SU more than 6? No, right? No. So answer no. So SP. So in this case, we get, I guess, same answer as the other classification system. Okay. Now let's do two more soils, and then we finish. So in this case, you will see that we're going to have different answers compared to the other classification system. I'll do soil C, and then you will help me with soil D. Okay, so we'll start with soil C. Again, we'll look at the amount of fines. We have silt 27, clay and 7, so we have less than 50%, right? Less than 50% fines. So in this case, still we're going to use this top table. Then we'll look what we have more gravel or sand. Well, in this case, well, if we have the data according to this sieve, this boundary, in this case, that should be okay. But if we recalculate, you will notice that you will decrease amount of gravel and increase amount of sand. So this one, you need to be careful, it's kind of boundary case. But let's assume that we recalculated based on the different boundary between gravel and sand, and we get these results. So in this case, we have more gravel than sand. We are going with the gravel here. And again, we'll look at the amount of fines, and fines it's 34% this way. And now we need to decide this question. You see, it says plasticity index, is it above A line or not? So this 0.73 times liquid limit minus 20, that's a mathematical expression of this A line. Remember a few slides ago when we talked about we weren't sure if it's CI or MI. So the way to do it, you just put liquid limit here and then see if it's above or below PI. So if it's above PI, so it's going to be above A line. I mean, sorry, if PI is like if PI is greater than this mathematical expression of A line, so in this case, it's going to be above the A line and it's going to be clay. So if it's below, if it's not, if answer no, then it's going to be sealed. We already know that it's going to be above the A line because for this soil C, we know that it's already CL, right? We did this before. So we know that the point is here, it's above the A line. That's why we're going to answer yes. We answer yes, and it gives us a symbol GC. So it's going to be GC for this one. I think when we use the other classification system, the answer was GCL. So in this case, it's GC. I have this feeling that AASHTO soil classification system is more detailed. This one is a little bit simplified, this unified soil classification system. Okay, so can you classify soil D for me? And then we'll finish for today. Can you classify soil D for me? Nobody can do that, or you're really tired, guys? Okay, so then I'll just do it for you. Oh, let's do it together. So again, we'll look at the amount of fines. So we see if it's more than 50% fines, ML. Okay, let's see if it's ML. So let's see how much fines we have. We have sealed 64. Um, so we have fines 64 of sealed plus X21, which is 95% of fines. So this is of course more than 50%. So we're going to use the bottom table. Then liquid limit, is it more than 50% or less than 50%? Our liquid limit is 42.5, so it's less, no. Then if it's above A line or below A line, I think we decided it was yes, it was above A line. So it gives us answer CL. CL. Why is ML? When we look at that one, it was above the A line, like soil C and soil D, they both were clay. So there should be CL. Because this question is if it's above A line or no. So this 0.73 times liquid limit minus 20, that's the way we draw this line. So if PI is above, like more, then it's going to be clay, yes. My okay. Well, I think it should be like more 0.22.5. Remember, it was kind of like on the boundary. Like I couldn't decide first if it's above or below. So I think it should be. I think it should be above. Maybe you can use the calculator. I didn't use the calculator. I just look at it and it looked like above, but I think it will be good to have like more accurate values. You see, like some soils like easy when they're like really above or like way below. It's very clear. Some soils can be like really like on the boundary, and this is like lots of trouble. You're like if it's like on or a little bit below or above, so it's very difficult to say. So I think this should be probably check it later, or maybe I use my calculator. Just want to see. So we have 42.5 minus 42 points. What's the liquid limits for cell D? 42.5 minus 24, right? So 18.5. No, sorry, my mistake. So 42.5 minus 20, it's 22.5 times 0.73. It's 16, right? So, and it's still below. It's below the. It's below the plasticity index. Plasticity index it's 18, right? So yeah, it should be above. Yeah. So we have plasticity index which is greater than 16.4. So it's above. Yes. So it's gonna be clay. Okay. So we figure out. Okay. Well, that's it for today, and I think we have a good timing today as well. Just right on time. If you have no questions, just if you guys staying for the tutorial, we have tutorial from 12 to 1. If you already did one yesterday, that's fine. Then the quiz will be open tomorrow, I think from 6 in the morning, the whole day. Kind of similar thing to quiz, laboratory quiz 1. So good luck for that one. And have a good day.